Welcome. If you've been looking for a solution to your molar solubility problem woes, you've come to the right place. This video will cover a challenging MCAT general chemistry topic, solution equilibria. Today, you're going to learn how to deal with the terminology involved in molar solubility questions and how to solve those questions in a logical and efficient way. Further, after today, you're going to be able to figure out how a common ion might change the molar solubility of a compound. Let's get started. Let's dive into that question stem. What is it that you're solving for? We're solving for a change in molar solubility with a change in pH. Molar solubility is the amount of a given substance or compound that's dissolved into a solution in order to saturate that solution, and it can change when changes are made to the system. The related constant, KSP, also called our solubility product, is an equilibrium constant, and that doesn't change when changes are made to the system unless the change is a temperature shift. So, if you wanted to consider how molar solubility might change in a new situation, you'd first want to know what the solubility product was for that system. Calculations for these solubility problems have a very characteristic structure you should be able to work with because you're going to see it on test day. You already know that solubility product is known as KSP, but you should also recognize that molar solubility will be written as X in KSP equations. Let's use this information in planning your attack on the question posed in the prompt. The problem stated that the solid that we were dissolving was iron 3 hydroxide. You would expect this to dissociate into two ion types, iron ions and hydroxide ions. If one iron 3 hydroxide molecule dissociated, how many daughter ions would dissolve? It would dissociate into one iron 3 plus ion and 3 hydroxide ions. In general, MCAT solubility problems will have X values far less than 1, meaning that only a small amount of the solid will dissociate when put in solution. Without even running a calculation, this allows us to predict that KSP, the solubility constant, will also be very small. On test day, you may have to demonstrate this relationship to be true quantitatively. KSP is a type of equilibrium constant, meaning that you can think about the KEQ equation when considering a KSP problem. However, KSP problems always have a pure solid as a reactant. There will never be a denominator in a KSP equation, because solids are not included in equilibrium constants on any system. This means that KSP will always be set equal to the concentration of products only. What would be the equation for KSP in this system using the same rules as we use in KEQ calculations? We know that ions are always raised to the power of their coefficients in K equations. So our equation would be the concentration of iron multiplied by the concentration of hydroxide cubed. We have to remember to include that cubed value because that's how we represent the coefficient when we're doing equilibrium calculations. Here's where molar solubility finally comes in. Molar solubility is the moles of a substance that dissolves. So in this case, we can set the amount of iron 3 hydroxide that dissolved equal to X. For each iron 3 hydroxide molecule to dissolve, there's X amount of iron ion released. In addition, there's 3X amount of hydroxide released. We can actually look back at the figure to see this. Each iron 3 hydroxide dissolving created 3 hydroxide ions, which means we have to multiply X by 3 when we're trying to calculate how much OH we formed. So KSP is equal to X times 3X cubed. Multiplying through, this gives KSP is equal to 27X to the 4th power. The question stem said that molar solubility is 9.94 times 10 to the negative 10th molar. Using your math and estimation skills, calculate KSP. You should plug in a rounded value for X, as MCAT math won't require extreme accuracy. After simplifying, KSP is equal to 2.7 times 10 to the negative 35th power. You've now demonstrated our earlier statement about KSP with math. If X is less than 1, KSP is less than 1 as well. In this case, the original solid dissolved into those 4 daughter ions. In any dissociation reaction, the original solid will split into at least 2 separate ions. This allows us to take our earlier conclusion a step further. If molar solubility is less than 1, as it's going to be for your MCAT problems, then KSP will always be equal to some value less than molar solubility, because any number less than 1 raised to a power becomes an even smaller number. You already demonstrated this mathematically as well. Molar solubility X was 10 times 10 to the negative 10th, which gave us a KSP that was much smaller, 2.7 times 10 to the negative 35th. Now let's consider the original problem again. The prompt stated that pH was increased to 10. What does this tell us about our ion concentration in solution? pH is inversely related to hydrogen ion concentration, and it's directly related to hydroxide ion concentration. So as pH goes up, hydrogen ion concentration goes down, and hydroxide ion concentration goes up. If you consider this related to the solution containing iron 3 hydroxide, a rising pH means more hydroxide ions are going to be around in our solution. This represents functionally an increase in our concentration of product, specifically that hydroxide ion product. We would expect, thanks to Le Chatelier's principles, that this reaction is now going to be driven back towards reactants, decreasing the amount of iron 3 hydroxide that's able to dissolve. So we can see it should literally go back to being a solid. If dissolution goes down, then the value of solute dissolved molar solubility would go down as well. Now that we've dissolved your concerns about molar solubility problems on the MCAT, you're going to be able to remember those unique terms for the questions and how to use them. Further, you'll be able to use the definitions of molar solubility and KSP to solve any calculation or critical thinking MCAT problems. And you'll even be able to handle tricky common ion effects. Make sure to practice this again within the next few days so that you'll be able to reliably solve these problems on test day.